Now, we've talked about this in class, but a lot of times people need to hear this a number of times and perhaps a couple different ways to really understand what we're trying to get at in terms of quantum numbers. These quantum numbers come out of the Schrödinger equation, and they help to explain where the electrons are in an atom. And while it seems like an unintelligible code, I find it to be really useful to form the basis of how electrons fill into atoms. And we're going to talk about that next in terms of electron configuration, which is the organization of the electrons in an atom. And so, again, as we've gone over in class, there are 4 different quantum numbers. The principal quantum number, and that's the energy level. The possible values for that are positive integers, so 1, 2, 3, 4, 5, and so on. And this has a symbol of n. Angular momentum quantum number has a symbol of kind of a lowercase script L, but you can also just use a lowercase l, and it essentially is telling us what kind of orbital or what the shape of the orbital is that the electron is located in. And so you can think of the principal quantum number as being the shell, okay, the energy level, and then the angular momentum quantum number being the subshell. So it's within an energy level, but there is a division within that energy level. And the possible values start at 0 and they go up to n minus 1. So in the first energy level, 0 is the only allowed value. In the second energy level, we can have 0, we can also have 1, because 2 minus 1 is 1. And so the next quantum number is the magnetic quantum number, and that tells us a couple different things, and I've got some images that I hope will make this make a little bit more sense. But it gives the orientation of the orbital, and it defines, if you're writing a set of quantum numbers for a given electron, it defines which orbital that electron is actually in. Remember, I used this idea of a mailing address, and that's the way I think about quantum numbers. So the possible values are negative L to positive L. So for example, if the L value is 0, the M sub L value can only be 0. But if L is 1, you can have M sub L be negative 1, 0, or 1. And so in some ways, this also defines how many of each type of orbital are around. The spin quantum number is one that essentially electrons can have only 2 possible spins, up or down. And so the possible values there are plus 1/2 and minus 1/2. And so looking at each of these, so again, principal quantum number, this is energy level. The Bohr model basically defined what this was. Again, electrons are in specific energy levels. However, within that energy level, things are broken up into subcategories that we call subshells that are different types of orbitals. And so the angular momentum quantum number helps to define that. And so the 4 types of orbitals are shown here on this image. An s orbital is a sphere. P orbital kind of looks like a dumbbell. D orbital is kind of like a double dumbbell. F orbital has a weird shape. You're not going to really be responsible for that, but I did find an image there. Now, the important thing to note is the code for this. The s orbital is the simplest one. The L value assigned for that is 0. A lot of people make the mistake of assigning that 1 because it's the first one. But this code starts at 0. So you've got to remember that s orbitals have a L value of 0, P has a L value of 1, and so on. And so you can see how the code is put together here. And so again, that's telling us what kind of orbital or the subshell. The magnetic quantum number, again, it can go from negative L to positive L. And the reason I have these images here is because if L equals 0, which is an s orbital, the only value that's possible for M sub L is 0. So that tells us there's only one possible value, so there's only one possible orbital. And that's what's shown here. And there's only one orientation. A sphere, if you turn it around, it's still a sphere. Okay, there's no different way to orient it. Now, the L value of 1 is a p orbital, And it can have m sub l values of -1, 0, and 1. So we could call this -1, 0, and 1. So in some ways, it's defining that we can have 3 p orbitals in any given energy level. When L equals 2, we have -2, -1, 0, 1, 2. We can have 5 of those types of orbitals in any energy level. Okay, but also remember that in the first energy level, only S is available because M or L can only be 0 to n minus 1. So this is the only thing available in the first energy level. In the second energy level, the S and P are available. In the third energy level, S, P, and D are available. And beyond that, the S, P, D, and F are available. Okay, and so now we're starting to see some structure build into where these orbitals exist. The spin quantum number, again, the electrons can only spin in 2 possible ways, and so we put a plus and a minus 1/2 there. Another thing that's important to note is something referred to as the Pauli exclusion principle, and what that says, and I don't have a slide for that, and I don't know why I didn't put a slide in, but the Pauli exclusion principle says that no 2 electrons in a given atom can have the same 4 quantum numbers. They can have 3 of them be exactly the same, but they can't all 4 be the same. And so what that sets us up for, because we have plus 1/2 and minus 1/2 as the 2 possible values, what this tells us that any one orbital can only have 2 electrons in it. And so if we look at this, this kind of gives us this relationship. So in the first energy level, the only thing we can have is 0, so we can only have s orbital. Okay, the possible value for m sub l is right here. The total orbitals in a subshell is 1, therefore only 2 electrons can be in the first energy level because, again, any orbital can only have 2 electrons. As we move up, this can have, because 0 to n minus 1 gives us s and p orbitals, and we can have a total of 4 orbitals, or 8 electrons, but 1 s orbital and 3 p orbitals. And you can see it grow as we move into higher energy. And that adds to the complexity as well as just the hierarchical structure of how this works. Okay? And what's interesting is that if you look at the periodic table, you can see that there are 2 columns over here on the left. And as it turns out, those elements, the outermost electrons, are filling s orbitals. So we call this the s block. Okay? And again, in any s subshell, we can only have 1 orbital, therefore 2 electrons, and therefore 2 elements there. The P, you can see 1, 2, 3, 4, 5, 6. Okay, 6 elements there. Again, if you look back, we can have 3 orbitals in that subshell, and that gives us a total of 6 electrons. And just looking here, you can see there are 5 d orbitals, and if you count this, which is not counted here, but there are 10 columns. Okay, so this is pretty awesome. The periodic table is helping us put all of this together in terms of where things are. So, for example, all these, the elements here, or the electrons that are going in here, n equals 2, L equals 0, m sub L equals 0. Okay, in this case, n equals 2, L equals 1. We can have different. We can either have -1, 0, or +1 for the m sub L. Okay, and so all of these things kind of fit together, and it might take talking about electron configuration to really gather how this works. Some of the types of questions that are going to show up are, which of the following is a possible set of quantum numbers for this element, or which one are not possible? And we'll talk about those here in class. So again, for summary, this is just the quantum numbers that define the electronic structure of an atom.